Okay, today we're going to talk about polyhedra, polyhedron, and some formulas we can use that work with three-dimensional shapes. So first off, what is a polyhedron and how does that differ from like a prism, pyramid, and all that? So a polyhedron is a shape that's formed by four or more polygons that intersect at their edges, and these don't have to be the same type of polygon. So these could be pyramids and prisms, but they can also be, if you look below at this shape here, this third one, on the right, you can see it's a bunch of triangles put together without having a specific kind of lateral face or base. So it's kind of neat. We can kind of move on beyond specific prisms and pyramids to talk about polyhedra. Now, what's really important is for a shape to be a polyhedron, it has to have polygons as its faces, which means they have to have edges. So anything that has curves is not a polyhedron or a polyhedra, right? But anything that actually has straight intersecting edges, and you can see they meet nicely at vertices, it doesn't have to be a prism, it doesn't have to be a pyramid, it can be something kind of wacky, it's still a polyhedron. So if you imagine if you've been to Walt Disney World and you've seen that Epcot Center, right, with all those kind of polygonal shaped windows or something like that, right? That's a giant polyhedron if you completely closed it. A soccer ball is a polyhedron, and your pyramid is a polyhedron. So the first thing we can do with polyhedron is talk about Euler's formula. And what this does is it doesn't kind of solve for anything, but it's a way for us to check the number of vertices, edges, and faces of our polyhedron. So what it tells us is for any polyhedron, if you take the number of vertices, subtract the number of edges, and add the number of faces, it should always equal 2. That's a rule that will always work. So vertices minus edges plus faces equals 2. So I think that's kind of a very interesting relationship. And where you might use it, I think maybe perhaps if you're designing and you're like, wait, I want to put, 17 triangles together and add on 4 rectangles and 10 pentagons, and you want to know if it'll actually close and make a polyhedron, you can count, right, the number of edges, faces, and vertices and see if that actually works. So that's one way you can kind of look at that. But again, I think it's just kind of an interesting relationship, an interesting pattern that Euler came up with. So if all we need to do is use this formula and verify that it works, something like example 1 is actually very straightforward. We want to count how many vertices, edges, and faces we have, and then just check that Euler's formula works. So remember, vertex is the number of points. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 vertices. And then edges are each of these straight segments. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 edges. And then finally, the faces are those two-dimensional shapes. So like the hexagons and the rectangles here. So 1, 2, 3, 4, 5, 6, 7, 8. We should get 8 faces. Faces do include the bases. All right, so now we want to verify that V minus E plus F does indeed add up to 2. So show your work here. 12 minus 18 plus 8, is that 2? Negative 6 plus 8 is totally positive 2. Euler's formula does check out. Okay, another formula we can use specifically for a right rectangular prism is actually an extension of our distance formula. So kind of interesting thing to think about. If we want to calculate the diagonal length of a right rectangular prism, that's this D here. You can see it's creating a right triangle, but what's interesting here is it's not creating a right triangle with the length, the width, or the height that we actually can measure, but we need to use this diagonal on the bottom here, this X. How do we get X? Well, it's still a right triangle, X, L, and W. We're basically doing Pythagorean theorem. So what's neat about this is we can kind of put it all together, use your Pythagorean theorems, substitute to create one single formula where the distance equals, or that diagonal equals, length squared plus width squared plus height squared, where D is the length of the diagonal. And I'm going to be specific here. It's the diagonal of the prism, not the diagonal of the face. So it has to go from corner of the prism to the opposite corner, so straight through the middle, not along the side. And this works only for a right rectangular prism. And again, if you wanted to derive this, it's just basically doing your Pythagorean theorem twice, which is kind of cool. So If we look at example 2a, we want to find the length of the diagonal of a 6 by 8 by 10 rectangular prism. So we have a length, a width, and a height. So pretty straightforward. As always, if you're working with a formula, I encourage you to write the formula down first and then actually plug in your numbers. So the diagonal in this particular problem is going to be the square root of 6 squared plus 8 squared plus 10 squared, right? And then we can go ahead and simplify that. So that turns into the square root of 36 plus 64 plus 100. Remember, do your PEMDAS, right? We want to simplify inside the radical first, so you get one number inside the radical before you try to square root, because don't make that 6 plus 8 plus 10, because that is completely incorrect algebra. All right. So let's add up 36, 64, and 100. So we're going to get the square root of 200, which isn't a perfect square, but that's okay because we know how to simplify this down to 10 square root 2. Don't forget your units. Now, with any formula, we don't always have to solve for the diagonal. We can solve for any missing variable. So now, if in this second question, we're looking for the height. So we are given the other three numbers. As long as we know as long as we only have one variable that's missing, right? That we need to solve for, we can solve for it as long as we can plug everything else in. So if we look at this 12 by 7, so we have a width, we have a base, which is also, you can call that the length, and then we have the length of the diagonal, which is 15. We know our formula, D equals the square root of L squared plus W squared plus H squared. Plug it all in, right? So 15 equals the square root of 7 squared plus 12 squared plus H squared. Just be careful with your PEMDAS when you're solving this. So think about your first step. What I'm going to do is I'm going to go ahead and square both sides because I can't do anything if H squared is inside the square root. So let me get rid of it. I can square both sides. 225 equals, and then I'll simplify my squares here. That's 49, 144, and H squared. And then we want to get H squared by itself, so I can combine my like terms. So that turns into 193. And then I want to get rid of that 193, so I'm going to subtract it. So I'm going to get 32 equals H squared. And now we can solve for H. So please don't square root too early, right? Get that square, H squared equals to a number. And now let's go ahead and square root. And I'm not going to include a plus or minus. Why not? Because H is a length, so I don't want a negative length. So H is the square root of 32. And then ask yourself, does that simplify? If it does, let's keep going. And yes, it does, because it's 16 times 2. So 4 square root 2 inches. Okay. Now let's move on to the idea of graphing in space. So when we talk about space, I know a lot of us think about, oh, the stars and astronomy and galaxies and planets. But when we talk about space here, we're literally talking about a three-dimensional space, right? Versus a 2D plane. So space for us in geometry just introduces a third dimension. What we're doing with this is now we're introducing a third dimension. We're introducing a third axis. So remember, traditionally, we just have your X and Y axis. So here's my Y axis, here's my X axis, and they intersect at the origin at 0, 0. So that's two-dimensional. To add in a third dimension, we can draw in a third axis, which we'll call Z. And it'll still intersect at 0, but now that we have a third axis, we have a third number. Now we're going to have ordered triples, which is just X, Y, Z. So that tells you how much we move along each axis. So for example, if I am trying to graph the point, let's say 2, 1, 4, on each axis, I still have a number line, right? So here's 1, 2 on my X, and then I'm going to go up 1 on my Y, and then Z, it's up to you. Do you want positive to be back, negative to be the front, or the opposite? I'm going to put positive to the front, negative to the back. And then we're just going to go 1, 2, 3, 4 out. So what you're doing is you're still traveling. Okay, 1, 2, I'm going to go up 1, and now I'm going to follow along my z-axis 1, 2, 3, 4. So what's kind of hard to imagine, because this is drawing on a two-dimensional surface, right, rather than 3 dimensions, is that point in pink if you can see that right here, it's actually popping out at you because I've moved forward on the z-axis. So you can draw your own three-dimensional axis. You can also look at these pre-printed grids, so you can see down below, which kind of give you these guidelines. It's not going to be exact, but in this case, if you can't really read it, this is x, this is the negative side of x, this is negative y, this is positive z, and negative z. You can estimate going up and down 1 unit along the diagonal for z. It's not going to be completely accurate, but it'll give you a kind of a neater drawing. And there's, of course, lots of software out there that'll do these 3D drawings for you as well. So if we want to graph our 3D solids on a plane like this, or on a 3D graph like this, what we want to do is we want to find the vertices or some key lengths, right, to help us find all of those edges. So here in example 3, we're going to graph a rectangular prism with lengths 5, 3, and 4. So it doesn't really matter if you want to say length is x, width is y, and height is z. You can switch them around, but I would just decide I want my width to be my length to be x, my width to be y, my height to be z. That way I'm consistent. And then it's up to you how you want to start, as long as we start at the given vertex. So we're going to start at 0, 0, 0, which is right here. I'm going to have each of these intervals be 1, right? So that's -1, -2. This is +1. This is +1. So you have an idea of my scale. And then I'm going to go 5 along the x. So if my length is 5, I don't have to go 5 both directions. I just have to go 5 one direction. So I'm going to go 5 on the positive because that's how I'm choosing to do it. So 1, 2, 3, 4, 5. And then I know the height for the width for y is going to go 3. So I'm going to go along the y-axis and go 1, 2, 3. Because I know it's a rectangular prism, this bottom, or I should say all 6 of my faces will be rectangles because it's a rectangular prism. I should be able to create a rectangle which has opposite sides being congruent and all angles being right angles. So all I'm going to do now is take the point here at 0, 3, 0, and count 1, 2, 3, 4, 5. So I create another length of 5 units, and there's the bottom of my prism. Okay, and then once I get the one base, what I like to do is I like to rise up with the height. So you can also go down if you like, but I like to go up. So I'm going to count again approximately, go on one diagonal here is 1 on the z, so I'll use that. So 1, 2, 3, 4. And then from here, I'm going to basically build another identical rectangle. So I'm going to go 5 out on the x, which is going to the left here, 1, 2, 3, 4, 5. Going 3 here along the right, which is my y. And then finding that 4th point. And there is that floating parallel base. So all I have to do is connect it from vertex to vertex, going up to down, top to bottom, and there's my rectangular prism. Okay, so you can do this for pyramids, you can do this for cylinders and all that. It's something to think about. So if you're interested and you have questions, please ask me if you have some questions on how to do the other shapes. Finally, other formulas we can use. So we talked about the diagonal of your rectangular prism, and that uses Pythagorean theorem, which is also related to just distance in general in 3D. So if you remember, our distance formula in 2D was d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, right? That's 2 dimensionals. 3 dimensions, it's actually really easy. Just tack on the z's. So now we'll have z2 minus z1 squared. And this is also related to what we saw in that rectangular prism diagonal formula. It's basically just 2 Pythagorean theorems, right, that we're doing here. So midpoint, same idea. The midpoint formula originally was just x1 plus x2 divided by 2 and y1 plus y2 divided by 2. Now, if we add 3 dimensions, we just add the z on. Easy peasy, all right? So example 4 is just using these formulas. So I'll just work this out to show you it's basically the same thing. And there you go. So if you look, it's just basically the same thing we've been doing all year long, just adding in the z's, the 2 z's, z2 and z1. One thing I forgot to do was to rewrite the formula since I already have them up there, but just remember when you're doing your work, it's always a great habit to write your formulas down. Always simplify as much as you can. I'm okay if you leave the improper fraction rather than making it a decimal. All right, thanks for listening.